Good afternoon, all my TIBSC friends, those who are preparing for the Savitribai Phule Pune University final examination for the semester number 6. And in earlier two videos, we have discussed few multiple choice questions based upon the syllabus of this nuclear physics paper. Today, in spite of going for all these multiple questions or numerical questions, we will go for some conceptual based questions over which there can be several different types of MCQs or multiple choice of questions can be asked. So once you understand these concepts, then it is very easy for anyone to understand or to solve the MCQs in any of the examination. So let's go to the questions one by one. First and most easy question is, what is energy equivalent of one atomic mass unit? For that we must understand what is atomic mass unit. So 1 AMU, an atomic mass unit, is taken in nuclear physics is equal to total mass of 6C12 carbon atom in kilograms, and this is to be divided by 12. That is the total number of nucleons contained by the carbon nucleus. And if this mass is calculated, or if this number is calculated, division is carried out, this comes to be 1.66 into 10 raised to minus 27 kilograms. Note that all these numbers are very small to actually measure as well as to manipulate or to use these numbers for several different calculations, and that's why physicists have used another method that is called as mass energy equivalence. Mass energy equivalence, or this is nothing but our relationship E is equal to mc square, the important relationship which connects mass and energy here. So if I use this formula here, E is equal to mc square, to calculate energy, it will come in joules. So therefore equivalent amount of energy for 1 AMU is equal to 1.66 into 10 raised to minus 27 kilograms into 3 into 10 raised to 8 meters per second, and square of this. If this entire number is calculated, this will have its units in the joules. I further can divide this energy, equivalent energy, by the 1 electron volt unit, and for that I have to divide this number by 1.66, sorry, actually 1.59 into 10 raised to minus 19. Actually this is coulombs into volt. That is the charge of the electron. If it is accelerated through a potential of 1 volt, this much is the amount of energy gain. So this is electron volts. So if this entire calculation is done, then we come across this final number is 931.5 MeV. So this is the equivalent amount of energy for 1 AMU. That is what we understood. 1 AMU is equal to 931.5 million electron volts. So henceforth in nuclear physics we use this very convenient unit to measure masses of all elementary particles, nuclei, nucleons, and so many things, and that makes very easy to solve the problems associated either energy released, energy absorbed, or whatever other kinematics of reactions. So this is one convenient method that is to be used here. Second question is, what are nuclear forces? This is from chapter 2. As we all know, in the chapter 1, the constituent of any nucleus are these neutrons and protons, and neutrons and protons can be in a very large numbers inside a heavy nucleus or any ordinary nucleus. And what is the force that holds all these nucleons together in such a very small space within the nuclear diameter of this particular nucleus, diameter of the nucleus? That is called as the nuclear force. So this force has certain attributes or certain properties. We'll see that later on, but before that let me make it you aware about that this force is existing between neutrons and protons. It can be between neutrons and neutrons, it can be between protons and protons. So thereby these several different types of three different types of pairs may exist inside this case, and thereby this force is responsible to overcome the repulsive force because of the same charges of the protons together, and that's why this nucleus can get a stability. So this nuclear force is responsible to make the nucleus stable, and therefore this nuclear force has several other following attributes on which there can be few questions in the multiple choice of questions. So first important property is that this is strongest of all four natural forces, that is electromagnetic, weak force as well as gravitational force. This force is strongest of all. Then second is this force is charge independent. As I said just now, that it doesn't depend whether you are getting this force between proton proton, neutron neutron, or neutron proton, whatever may be the pair, the force is same for all such type of pairs. Then third is this is non-central force, another very important property of this. Then this is saturation type of force, that means very few limited number of nucleons can have bonds with the particular nucleus, so all the nucleons inside nucleus do not have bonds with each other. In that sense, this is a saturation force. Then this is spin dependent force, depending upon the spin of these particles. Actually all these are fermions, and depending upon that there varies the magnitude of this particular force. This is spin dependent. So these are the 5 different properties associated with the nuclear force which gives rise to the stability of the nucleus, and that's why it is very important force of the nature. Then question 3, what is the function of cadmium or boron rod in nuclear reactor? In any nuclear reactor, usually we carry out this fission reaction where a 0n1, a thermal neutron, is incident upon. This is called an incident particle, and this is 92 uranium 235. This is called as fissionable material. It undergoes fission and forms 2 different nuclei of intermediate masses 1 and 2. I am calling this to be A and B. Several pairs can be seen there. Along with that, 3 more fast moving neutrons are generated. Now these neutrons can carry out further fissions, and if we are not able to control this rate of the reaction, then the reaction may become uncontrolled chain reaction, and that is the case of the atomic bomb. Not to that, in that reactor, if this thing says happen, then it will explode immediately. Not to happen that some of these fast moving neutrons are to be absorbed, and this absorption is done by this rod, either made of cadmium or second material used is this boron. So both these rods or these materials, these elements have high absorption reaction cross section for fast moving neutron, high absorption reaction cross section, and thereby they can easily absorb some of the neutrons, and on an average, that means in this particular nuclear reactor, after every single fission reaction, 1 neutron is allowed to go for further fission, and remaining 2, out of these 2 neutrons are to be absorbed and 1 is allowed to go further, and this absorption is done by these materials which are called as cadmium and boron rods. So these are essentially called as the control rods. By inserting these rods inside more and more inside the nuclear reactor, core of the nuclear reactor, we can decrease the number of neutrons available, thereby rate of the reaction can be controlled, or pulling out them out of this nuclear core of the reactor, then the rate of the reaction may be increased. So these type of materials play a very vital role in the functioning of every nuclear reactor, fission type of reactor, where this process goes on, and thereby controlling the rate of the reaction, controlling the rate of the reaction itself is one of the very important function of all the control rods which are made up of cadmium and boron. Then next, which quantity determines the size of the nucleus? For that case, in the chapter 1, you might have studied this relation. This is R equal to R0 times A raised to 1 by 3. This equation we have obtained from Rutherford's alpha particle scattering experiment, in which this is called as nuclear radius. So nuclear radius R is given by R0, that is this R0 is the radius of one H1 or the hydrogen nuclei or single proton, and this is practically, if it is measured, it comes to be 1.5 Fermi. Fermi is 10 raised to minus 15 meters. That is another unit used to measure the nuclear dimensions, and therefore depending upon this a nuclear radius may go on increasing. As for smaller a, this R will be smaller, and for large a value, again this will be larger. For example, 6C12, this radius of 6C12 carbon will be something different, and if I go for 92 uranium 235 or 38, in this case total number of nucleons will be 238. So this radius of uranium will be much bigger. So you can calculate here R0 times 12 raised to 1 by 3, and this is also R0 times 238 raised to 1 by 3. Of course, this RU will be much bigger as compared to RC or carbon radius, and therefore the quantity that determines the size of the nucleus is nothing but the mass number, that is the capital A, or atomic mass number, that is capital A. So there can be one or two questions based upon this type of simple empirical formula or the nuclear dimensions as given by this Rutherford experiments. Then next, what is the order of nuclear density? In physics, we calculate density by the simple equation. Density is nothing but mass upon volume. Now, as we got the expression for radius here, we can find out, assuming that this nucleus is usually a spherical radius, spherical shape, then we can calculate here density rho by mass is the number of protons plus number of neutrons multiplied by mp. So that is A multiplied by mp or mn, we can take. This is the total mass of the nucleus. How many number of nucleons multiplied by mass of each will be multiplied by that, and this is given by 4 by 3 pi into r cube, and further calculations gives you A times mp, mass of the proton or mass of neutron, you can also take. So this is 4 by 3 pi, this is r cube will give you r0 cube. So this is a constant here multiplied by A again. So here this A raised to 1 by 3 raised to 3 will be A. So this A gets cancelled. This is constant and everything of this is constant. So this attains a constant value, and this comes to be around 10 raised to 17 kilograms per meter cube. So you can imagine how large this number is if we know the density of water. Density of water is a very small number in comparison to that, 10 raised to 3 kilograms per meter cube. So if we compare these two numbers, then you will find that nuclear density is 10 raised to 14 times more than the density of the water. So you can imagine in a very small space a large amount of mass of nucleus is concentrated, and therefore it is said that more than 99.99% of mass of atom is concentrated in nucleus. Okay, so concentrated in nucleus, whereas all the remaining electrons which are revolving around the nucleus, they carries a very small fraction of entire mass of this atom. So that's what in an atom the entire mass of the atom is concentrated into its nucleus. That is what question 5. Now question 6, the binding energy per nucleon curve is sharp for helium. What does it show? So this is one characteristic of this binding energy curve. You might have drawn this earlier in this classroom. This is what a curve between, this is the mass number and this is binding energy per nucleon, or the amount of energy released in a nucleus divided by number of nucleons. In that case, this is called as also specific binding energy. If this curve is plotted, this curve shows a various as this type of spikes we have seen, it goes increasing, reaches maximum, and then starts falling again. So here this element is ferrous iron, which is said to have maximum specific binding energy, that is 8.53 MeV. Whereas for all other elements, this number goes on decreasing as we go for this smaller E values, and here also for bigger E values, this number also goes on decreasing, and that what suggests is there are certain spikes on this curve. These spikes tells you something very interesting fact, like for helium, and there's this elements here like helium, as I said, there are three elements close to the helium, two elements of course. So first one is 1H1, second is twice He4, and third is 3Li7. so if on this graph, if I plot this, this will be helium, hydrogen will be here, and lithium will be here. So that suggests these elements which are having their mass number in the proportion of 4, that is 4, 8, 12, 16, 20 and so on, these elements in this first region less than Fe, these particular elements does not lie on the smooth curve, but there are certain spikes to be observed, and these spikes suggest that these elements are extra stable. They have some more binding energy per nucleon as compared to their neighbors, so there is some extra stability associated with that. So these elements like helium, etc., these elements are said to be extra stable as compared to their neighbors. So this particular curve suggests you this particular fact, okay, their neighbors. And apart from that, we also might have studied that this particular region where a light heavier nuclei, if it is broken into two smaller nuclei, here binding energy per nucleon gets released. So that is the process which is called as fission process. So fission is shown here for heavier nuclei, whereas in case of lighter nuclei, when two small lighter nuclei come together and they form a heavy nucleus or bigger nucleus, in that case also there is a loss of binding energy per nucleon, or that energy is released in this process. So this is called as the fusion region. So fusion, for fusion where lighter nuclei come together and they form bigger nucleus, energy is released. In fission, heavier nuclei is broken and gets converted into two smaller nuclei. In that case also binding energy per nucleon, whatever this difference, that is released in that process. So both this process of fission and fusion can be understood on the basis of this binding energy per nucleon curve as shown in the diagram. Then question 7. What is the radius of nucleus of mass number 64? It's very simple. Again you have to use R is equal to R0 times A raised to 1 by 3. So as we know, this R0 is 1.5 Fermi into A is 64, that raised to 1 by 3. As we all know, 4 into 4 into 4, that is third power of 4 gives you 64. Therefore 64 raised to 1 by 3 must be equal to 4. So if I use it there, then this becomes 1.5 into this is 4, and therefore it becomes 6 Fermi. So this is the radius of that element which is containing 64 number of nucleons. This can be calculated by this formula which is called as semi-empirical mass formula. Again we are coming across same question, define atomic mass unit or AMU. That is what we have in the first question only we have discussed this. 1 AMU is given by this standard method, that is mass of 6C12 carbon atom, okay, mass of 6C12 in kilograms, divide this by total number of nucleons contained by this 12, and this is how, as we said here, it comes to be 1.66 into 10 raised to minus 27 kilograms, and this amount of mass in kilograms is called as 1 AMU. And as I said earlier, when it is converted into energy, its energy equivalent is given by 931.5 MeV. So there may be few questions, multiple choice questions based upon this particular fact as well. Then why, question number 9, why nuclear forces are called exchange forces? So as we all know, all fundamental forces in the nature, they arise, or their forces are possible because the in between interacting particle there is always something gets exchanged from here to here and to here to here. Suppose this is a positive and this is negative charge. In case of electromagnetic force, we have this gamma particles or gamma photons which continuously interchange between them, and that's why this is called as the exchanged force. Now in case of strong nuclear force between this proton and neutron, so actually these protons and neutrons are made up of, in bigger picture we can go for, there are three quarks, U and D, and whereas here U, D and D. Now these quarks undergo this type of strong interaction, and there is exchange between these quarks here. So these quarks and these quarks, there is a continuous exchange, and these particles are called as gluons. So the particles which exchange between quarks and thereby these nucleons remain together and this particular force comes in existence. This is possible because of this exchange particle gluons, and that's why the strong nuclear force is called as exchange force. So for like electromagnetic, like gravitational, like weak force, the strong force also is an exchange particle force, and that comes in existence because of this process which is called as exchange of an intermediate particle. Then nuclear, question number 10, nuclear forces are saturated forces. Why? As I said earlier, in any nucleus, as we discussed here, suppose this is a proton here and this proton and another proton on this boundary, there may not be existing force or a attractive force between these two, because at that distance there may be a possibility that these two forces, these two protons may repel with each other, but in between there are certain number of neutrons and protons are possible, and this number here is only limited number. So given any number, any nucleon here, this nucleon is connected to limited number of nucleons, and thereby it is shielded from this nucleon and this nucleon. They won't have any interaction because of in between. In that sense, this is called as a saturation type of force. So all nucleons are not associated or connected with the all other remaining nucleons. Limited number of nucleons have bonding between them, and therefore this property of saturation force comes in picture. So that same thing can be observed in molecular physics too, but here in nuclear physics, in nucleus, this tendency of the nuclear force, that is saturation property, plays a very vital role in the stability of the nucleus. That is to be understood. Again, question number 11, give an example showing the conversion of energy into mass. As already we have seen, E is equal to mc square, this relationship given by special relativity. Some amount of energy, or whenever there is certain mass, if this mass is converted to energy, this conversion is given by this formula E is equal to mc square. There is one very specific and typical example which is called as pair production. That means from energy or from photons. I am drawing this diagram here. These photons are coming in, and when this particular photons comes in the vicinity of some heavy particle or nucleus, then there is a possibility that this gives rise to two elementary particles. One is called as E minus, that is electron, and second is called as E plus, that is called as positron. So actually this is positron and this is the electron. These are antiparticles of each other. So antiparticles of each other, and hence this is I can call this the antimatter, and this can be called as matter. So this is the matter of which we all are made up of, and there can be an antimatter where there exists every single antiparticle to every single particle in the matter. So here positron and electron are antiparticles of each other. So from this energy, these two particles are created. This is the process which is called as pair production, where energy gets converted into mass. If I know their energy, in this case energy equivalent is 500.5 MeV, 51 MeV. This is also exactly equal 0.51 MeV, having same mass. So I can understood that there must be at least 1.02 MeV photon is needed to create one electron and one positron. So this is the conversion of energy into mass, and conversion of mass into energy is also known to you, and that is also related to the next question number 12, that is the mass defect. So what do you mean by mass defect? That can be calculated here again. Earlier we have known that this mass defect is given by mass of individual nucleons, so that is MP times Z, number of protons, plus Mn times neutrons, that is Mn. We always found that this mass is more than the actual mass of the nucleus, which is containing A number of nucleons and Z number of protons. So this mass is always more, and whatever mass lost in the process of formation of the nucleus, this is called as the mass defect. So whenever nucleus is formed, this mass is always found to be more than the actual mass of the nucleus, and this mass is called as the mass defect, and therefore binding energy is nothing but multiply by this delta M by C square, or we can get the amount of energy released in joules. And if you want to calculate this binding energy in nucleon in million electron volts, then just get this multiplied by this delta M by 931.5 MeV. That is the amount of energy equivalent to 1 AMU. That gives you directly binding energy in million electron volts. Note that during the formation of the nucleus, this much amount of energy is released by the nucleus, and therefore nucleus gets a stability. In that sense, it is called as binding energy. To disperse this nucleus into its constituent again, same amount of energy will be needed to be provided from external sources, and then it is possible that this nucleus may undergo a breaking process, and individual protons and neutrons will be created. In this case, the reverse is also possible, what we have seen in the case of formation, and this entire thing is called as mass defect. Question number 13. What do you mean by the fissile material? So as I said, in all the nuclear reactors, primary type of nuclear reactors, we have shown this is the fission reaction carries out. So incident neutron 92 uranium 235, and this gives rise to this further reaction, plus on an average 3 new neutrons, fast moving neutrons are created there. Here this material is called as fissile material. So the material which undergoes the fission reaction is called as fissile material. We know that in natural uranium there are two entities existing, uranium 238 as well as uranium 235. If we go on actually finding the proportion of this uranium existing in nature, you will find that for 144 atoms of uranium 238, we find there is one atom of uranium 235. So this particular proportion tells you in natural uranium, most of the 99.9 more than that percent amount is this uranium 238, which is not useful for this type of reaction, so it is unfissionable or non-fissionable, whereas this is fissionable, which is found to be in very small proportion as compared to this uranium 238. So this is a fission material or fissionable material. Now depending upon the type of nuclear reactor, size of the nuclear reactor, its capacity, that means the energy conversion capacity, energy creation capacity, generation capacity, this fissile material size can be of different size. That means to what extent, to what we need, what amount of energy we are needed to as an output. Based upon that, this critical size of fissile material can be decided, can be calculated. So that is called as nuclear reactor engineering. So we won't go into details of that here, not needed. Then what is the function of moderator in nuclear reactor? Earlier we have seen that is called as the control rods. The function of control rod is to reduce the number of fast moving neutrons, reduction of the numbers, flux of the neutrons, reduction in the flux of the neutrons, that is the basic part that is done by the component which is called as control rods. Whereas moderators have a very nice function or important function that slows down fast moving neutrons, and once these neutrons are converted into slow moving neutrons, now these neutrons are made available for further fissions. So controlling is different thing, and taking energy of these fast moving neutrons and making that available for further fission, that process is called as moderation or moderating, and that's why these materials are called as moderator materials. Usually this D2O, or that is called as heavy water, or sometimes this ordinary water also works as a good moderator. There again other elements also can be used, materials also can be used as a moderator. Here these elements have such a size, this nuclear size is such that this is exactly having size in the range of the size of the nucleus, and therefore the maximum exchange of energy is possible between this. Suppose this is a D2O, here it is a and this neutron. Now this proton neutron or this neutron proton etc., this type of interaction takes place, and where maximum energy from this can be taken by this material, and thereby this neutron is slowed down, and once it is slowed down, then it is made available for further fission. That's what, to continue the reaction in a continuous manner, we need to have these control rods to absorb excess number of neutrons, as well as some of the neutrons which are not absorbed, we have to reduce their energy, and to reduce this energy, these moderators function in any nuclear reactor. So that is what we have to understand in case of nuclear reactors. Then how does the nuclear radius of an atomic nucleus is related to its mass number? Again, this is a repeated question that we have seen. R is equal to R0 times A raised to 1 by 3. This empirical mass formula connects radius of the nucleus or diameter of the nucleus and its mass number as shown by this. So Rutherford alpha particle experiment, that scattering experiment, that suggests or that tells you this type of relationship is hold between all type of nucleus and their mass number as given by this. Then what is meant by specific binding energy? That is what already we have calculated or we have shown. This is binding energy per nucleon. Suppose this is capital A. To form any nucleus, that is 6C12, 12 number of nucleons are required, and if whatever energy emitted in this case, energy emitted in the case of formation of the nucleus divided by 12 number of nucleons, this will give to a binding energy per nucleon for this particular carbon atom. So that is what next example is exactly related to this. Binding energy of the nucleus of C12 is 92.17 MeV. So find its specific binding energy, which is given by binding energy per nucleon, and therefore it is 92.17 divided by 12. If this calculation is done, this comes to be around 7.68 MeV. So this is the specific binding energy of carbon. On the similar grounds, we can go for ferrous or iron. It comes to be 8.53 million electron volts, and like that. So for each and every element, this type of binding energy per nucleon can be calculated, and it is plotted as we have seen in the earlier case. This particular plot or this graph is called as binding energy per nucleon. So this is specific energy per nucleon versus nucleon number. This curve is this, and we can have several different types of properties of this. All nucleus can be discussed with the help of this particular curve that is already discussed by us. Now question number 18, in which nuclear reaction, nuclear fission or nuclear fusion, more energy per nucleon is released. So this calculations, for that again we have to go for calculating actual energy released in fission and energy released in the fusion type of reaction. So these reactions take place when two smaller nuclei come together and gives you bigger nuclei, whereas here this bigger nuclei gets broken into two smaller nuclei, and this is fission and fusion. If this calculation is done for any typical reaction, this comes about amount of energy released per nucleon is almost 20 to 30 million electron volts, whereas in this process the amount of energy released per nucleon is almost around 200 MeV or million electron volts. So this is more energetic way. So fusion is the more energetic way per nucleon if it is considered or if it is compared with the fission, and that's why this is the reaction in which more energy per nucleon is released as compared to the fission. So that can be through several calculations can be done for different reactions, and for every reaction it is found that fusion is more profitable as compared to fission, and that's why in all the stars and galaxies wherever this type of nuclear fusion reaction takes place, large amount of energy is released, which is taken by which we on earth we receive this energy from the stars. Next question number 19, what is radioactivity? Now look at this. Radioactivity is the phenomenon where this is natural and spontaneous this natural and spontaneous phenomenon, that means it doesn't, and it's a statistical too. So where this particular nuclei undergoes a decay, disintegration, so alpha, beta and gamma, these three different types of radiations may be given by that radioactive material, and this phenomenon is called as radioactivity. This is a natural, it is a spontaneous, natural in the sense and spontaneous in the sense it does not depend upon any external parameters like pressure, temperature, etc. So this is a property exclusively of that material, radioactive material, and this decay constant only decides the rate of decay and all further things. It's a statistical phenomenon. We cannot identify that a particular nucleus will undergo this process. So every time you have to talk in terms of probability, and therefore its half-life, mean life, etc. All these concepts are associated there. Now question number 20. What happens when a gamma rays are subjected to electric and magnetic field? So for that we must know the properties of this. So alpha particles are positively charged nucleus, that is nothing but twice He4 helium nucleus. Beta particles is negative charge particles which are basically electrons, and gamma particles are, these are simply photons, so these are neutral. So this magnetic and electric field does not affect these photons at all, so their path remains unchanged. So that is the actual answer we require here. So path of this gamma photons remains unchanged, photons remains unaffected or unaffected. So I think you have drawn this diagram earlier. Suppose this is a radioactive material where it is kept, and if this is a positive plate here and this is negative plate kept here, this radioactive material will give out this electron or beta particles will move towards this, alpha particles will move towards this. So this is beta towards positive plate, alpha towards negative plate, and these are the particles which are neither go toward this side or this side, and these are nothing but gamma particles which remains unaffected. So that can be understood from the radioactivity phenomenon as we have discussed earlier. Then how many disintegrations per second will require in 1 millicurie? So this Curie, Becquerel and Rutherford, these are the three different units used in case of radioactivity to measure the activity of any radioactive material. So in case of 1 millicurie, actually 1 curie is equal to this number is given to be 3.7 into 10 raised to 10 disintegrations per second. So if there is a radioactive sample and if it gives this number of disintegrations per second, then we call activity of that sample is to be 1 curie, and therefore 1 millicurie means 1000 part of this and that's what we have to multiply it by 10 raised to minus 3, and therefore 10 raised to plus 10 into 10 raised to minus 3 or divided by 1000 will get this to be 3.7 into 10 raised to plus 7 disintegrations per second. So that is how we can define this. Further, question number 22 is again related to that same. So Curie is the activity, that means whenever a radioactive material sample gives this 3.7 into 10 raised to 10 disintegrations per second, then activity of that is called to be 1 curie. So this is one unit. Similarly, there is another unit that is called as Becquerel. Becquerel is defined as 1 disintegration per second. Now this is very small as compared to this Curie, and this Becquerel is the another unit with which also we can measure activity of the radioactive materials. So therefore we can give question number 23 where we can find out the relation between Curie and Becquerel. These are the actual names of the scientists. Here we are using their units. We are using these names for the units. So 1 Curie is equal to 3.7 into 10 raised to 10 disintegrations per second, and as 1 Becquerel is 1 disintegration per second. So this is how this much. Okay, so this is 1 Curie, and therefore 1 Curie is equal to this many number of Becquerel. So this is 3.10 into 10 raised to 10 Becquerel. So this much 1 Curie is equal to 3.7 into 10 raised to 10 Becquerel, or 1 Becquerel is equal to divide this 1 Curie upon this, you will get that many number of Curie. So this is the conversion between relation between Curie and the Becquerel. Now question number 24, when an alpha particle is emitted, what is the change in atomic number and at mass number? So that's what whenever this alpha particle comes out of the nucleus, it gives you twice He4. So that shows this Z is decreased by Z minus 2 and this A is decreased by 4. So mass number decreases by 4 and atomic number is decreased by 2. So the new nucleus formed. Suppose there is a X nucleus which undergoes this alpha decay and Y nucleus is formed. So here Z, X and A, I'll get here to be Z minus 2 and Y this is A minus 4. So this is the new nucleus generated which will have this type of the mass number and atomic number. Then what is radioactive radiation used in the treatment of cancer? So in medical applications of this radioactivity, we might have heard or might have known that there is a very specific element, iron 131. So that is used, radioisotope of course. This is used a very basic element for treatment of various cases, medical treatments. Actually there can be large number of applications, so you have to read all these applications, medical applications for each and every nuclei, and what these nuclei are for used for a particular purpose, that can be understood easily then. Then question number 26, give the relation between mean life and decay constant. As we know, this relation between half-life, T half is given by 0.693 upon lambda, where lambda is decay constant, and this mean life is given by lambda is equal to, mean life tau, symbol used for that is tau, which is given by 1 upon lambda. Therefore we can connect between these two. I can write this T half is equal to 0.693 up into, this is tau, that is mean life, or the mean life is equal to t half divided by 0.693. If it is calculated, we get tau is equal to 1.44 times t half. That means tau is always bigger than half life of that particular material by 1.44 times. So this is how, this is the relation between, this relation between, they are, that means mean life and disintegration constant, they are reciprocal of each other. Half life and mean life of this disintegration constant, they are connected by this. So mean life and the half life, they are also connected by this relation, or they are connected by this relation. So any one of these four, there can be a numerical question, as well as there can be a multiple choice of question can be framed, so that is to be remembered in this case. Then last two questions are remaining. Question number 27. All the elements found in nature are not radioactive. Why is this property in heavy elements only? So again, there is a question of stability and instability. So heavier element, as we know that all these elements, for example 92 uranium 235, there are 92 protons, and it is very difficult to hold all these protons together. Therefore we require some more number of neutrons as compared to protons. So this number gives you excess number of neutrons are needed, and therefore this type of nuclei are little bit unstable, and to attain this stability, some of the nuclei undergoes a decay process. So alpha, beta, gamma radiations comes out of that unstable nuclei, and thereby it becomes a stable or non-reactive. So lighter element are more stable as compared to this heavy element, and therefore this stability tells you why, whether the nuclear particular element will undergo decay or not. That is this particular connection. And the last question, which is the particle emitted along with the electron when a neutron is converted into proton in a nucleus? I am sure you might have studied this beta decay earlier. Beta decay is the process where neutron gets converted into proton. So this is 0 and 1. This is 1p1 at hydrogen nucleus or proton, and plus 0e minus 1. So negative charge electron particle comes out there, and along with that, initially this reaction was not balanced. So energy conservation principle was violated by this reaction, and later on Fermi gave this particular method or this particular theory that along with this electron there must be some other neutron particle may be coming out, which is exclusively carrying some more energy, and this is called as anti-electron neutrino. Actually this is anti-electron neutrino. This is not electron neutrino, anti-electron neutrino. That is comes along with the electron, proton, and therefore the total energy is shared among these three, and therefore continuous spectrum of beta decay can be explained with help of this third particle, and that is the particle which is called as anti-electron neutrino. That is the necessity to conserve this energy conservation principle in this reaction. Otherwise this reaction doesn't balance, and it doesn't give you a correct picture of this particular case. So energy conservation, momentum conservation, this emergence of this particle nu e bar, that is anti-electron neutrino is must. So that is the theory in the beta decay which is given by this. So friends, these are the few questions we have discussed in today's session. I am sure there may be several numerical questions as well as several multiple choice of questions which you will find in the examination, which are based upon this. Also in the next few days I will come up with some other new questions, remaining questions of remaining chapters, and that also will help you to go strongly for this forthcoming examination, that is the SPBU multiple choice question of final examination. So thank you.